to start this day with a nice keynote from Michael Schwarz. This is my honor to welcome Michael Schwarz on the stage. Please proceed. He is a tenured faculty member at the CISPA Helmholtz Center for Information Security, where he works on system security with a focus on microarchitectural and transient execution attacks. He earned his PhD from Graz University of Technology, or TU Graz, and has been at the forefront of research into breaking modern CPU through software-based side channels and transient execution attacks, and so on and so forth, of course. Michael is part of the research team behind some of the most impactful hardware vulnerabilities of the past decade, including zombie load, which is my personal favorite, by the way, malware guard extensions, platypus, and last but not least, meltdown and Spectre. His work has significantly shaped how industry and academia understand and mitigate side channel attacks in real-world systems. Today's talk is about how modern CPUs can no longer be assumed correct, showing that the hardware itself can behave like a source of exploitable vulnerabilities. And this is from my LLM summary. Was it good? Okay, all right. We're delighted to welcome him today for the 10th edition, and please join me welcoming Michael Schwarz. Thank you.
So thanks a lot, and thanks for having me here. So today, I want to kind of bridge a bit the software security, hardware security, but bear with me, I will always stay on the software level, so it should be good to follow, even if you have like no idea about hardware. So does that work? Yes. So it was already nicely introduced, thanks a lot. Also zombie load, my favorite vulnerability, I have to say, but it's not part of today's keynote. So looking at my past 10 years, so I'll give you a bit of a context, which was already nicely summarized by this LLM, whatever you use there. So I started working essentially 10 years ago on CPU security and all these attacks. And we had quite some impactful things in these past 10 years. So with colleagues and my group, we discovered things like Spectre meltdown. We started this entire field of transient execution attacks. Then we pioneered architectural leaks from CPUs with Epic Leak, the first thing. We'll also see that today. And as you've already seen the logo yesterday in the talk, if you paid attention, we also showed that we can do power side channels purely from software in the CPU and leak secrets from that. And we have many of these CPU vulnerabilities that we discovered. Some of them I will talk about today. But of course also, some people always say like, we just want to see the world burn. Well, it's not entirely true. It's fun, yes, but we also want to make sure the world is a more secure place. So we also have defenses for all of these things, and you see defenses in production. So KPTI, for example, is one of the things. Probably a software mitigation, if you use any modern operating system on a decent CPU, you will probably have code running on your systems where I was involved to protecting you against the things that I discovered. So it's a good thing. So as a summary, all of you sitting here essentially, I probably broke your CPU, so probably all of you have a CPU in your pocket in front of you with any of these vulnerabilities and any of these defenses running on top of them. So this was my past 10 years, but I want to go a bit further back than that. So if you go back before that, even before I was born, talking about software exploitation, and I guess many of you are familiar with software exploitation. When I teach that in my software security classes, I typically start with this milestone here in 1988, the Morris worm, like one of these first worms, a famous one, that also used a typical buffer overflow back then. That was 1988, so a long time ago. That's like nearly 40 years ago. It's a long time now. And then we've seen this nice article, Smashing the Stack for Fun and Profit in 1996. I'm pretty sure a lot of you have seen that article, know it, have read it. And then we've really seen like a lot of advance in software exploitation. So first thing, we've seen mitigations. Then we've seen return to libc. We've seen mitigations, then chaining things and going into parts of libc for exploitation, fixing things, going to 64-bit. We needed some already gadgets to pre-fill things to then get the parameters for returning to libc. And then essentially in like 2007, depending on whom you ask, academic community or hacker community, but roughly around that year, we have seen return-oriented programming which is still a widespread exploitation technique. So we've seen, well, a lot of software exploitation out there, many techniques, different techniques, and still things that we do nowadays. And when I talk about that, it's like, okay, we always have like attacks, and then we have defenses and attacks and defenses. And a lot of people are like, especially if they're not coming from security, like, okay, it's a kind of a cat and mouse game, right? You're just creating your own jobs. You're breaking something, you're fixing it, you're breaking it, you're fixing it, and then you continue like that, so you have your well-paid jobs, and nothing improves. But I would argue this is not true. So essentially, we don't have this cat and mouse circle, but it's more like, I call it a security spiral. So yes, we have attackers, we have defenders, and attackers improve, but also defenders improve. We get better defenses, we get better attacks, we get better attackers, we get better defenses, we get even stronger attackers, we get stronger defenders, and we're maybe now somewhere here. We have super strong attackers, but we also have pretty good security in software nowadays. And maybe we don't see that, because if you look at the statistics and of exploits and articles that we see where something was hacked, where something was exploited, and the number of bugs just increasing. But, bold take, and well, it's a keynote, right? If you compare a system now with all the defenses we have in place and take an attacker from, let's say, 25 years ago, this attacker will essentially have no chance in exploiting a decent system. So yes, I would argue we are doing a good job in software security. We are making our systems more secure, and they're way more secure than they were like 20 years ago. And this is a good thing. So attackers back then, no chance. But now we have a new type of attacker. Suddenly, we have this super defended systems, and attackers can't do a lot. And then we get attackers not going for software security, but software attackers coming from a different level, going for hardware vulnerabilities. And there, for that, we essentially have no defenses. So we're completely defenseless against such a type of attacker. So continuing this history of software exploitation, we had all these techniques, and now we extend them with attacks for exploiting software, but using hardware vulnerabilities. So that essentially started in 2018 with Spectre and Meltdown, and now we see a very interesting trend with architectural CPU vulnerabilities, which started in 2022. So 2018 was kind of this landmark here, where we disclosed Spectre and Meltdown to the public. So some of you, especially if you work for a company, might have already known about it in 2017 when we reported that. This was really what changed a lot. And this shocked a lot of people, both in industry, in the academic community, but also, well, worldwide on the news. We saw that, like even CNN had a developing story about that. And suddenly, this mindset shifted, that we all, well, accepted that we have software, and software has bugs, and software is going to be exploited, and we have to update that. But before like 2018, it was like, but the hardware, this one is secure, why would it have bugs? Why would it have vulnerabilities? But since Spectre and Meltdown, we know CPUs can have security vulnerabilities too. So this was a surprise to a lot of people. And we also see that in numbers. So that was first like, okay, maybe this is a one-time thing. We have like one vulnerability, it's bad, we patched it. But if you look at the numbers, well, this essentially started back then. Taking two CPUs here, Intel CPUs, also because, well, Spectre Meltdown was first discovered on Intel CPUs. The left one, Core i7-6700T, one of my favorite CPUs. That's the one where I did my PhD. From 2015, it's essentially affected by like all the vulnerabilities that you can imagine. So if you ever want to reproduce something like zombie load or whatever, get this CPU. It's very nice. It's like full of vulnerabilities. And similar to software security, this also improves, right? So the right one is a rather recent one from 2024. We see it has way fewer vulnerabilities because, well, they are also fixed. We see the same improvements. We see the same spiral also in hardware. We find something, it's fixed. We find more, it's fixed. We find more, it's fixed. And we also see things that are, well, a lot newer. And also, parallel to like what we see in software security, we also see the different techniques of attacks when we're talking about CPU security. So it all started with side channels. We've seen hardware side channels long ago, but software exploitable CPU side channels that essentially started in 1996. And there, with these side channels, we've also seen that in talks, for example, yesterday, you always measure something indirectly by seeing power consumption, by seeing timing differences, and then you don't directly get the data out of that, but you have some signal, and from that you infer some data. So you just get the metadata, some data about the actual data. And we've known that for a while, and also CPU vendors said like, okay, whatever, just write your software in a way, also this discussion was here yesterday, in a way that this cannot be exploited, and that's fine. And for some types of side channels, or for most of them, you can actually write the software in a leakage-free way. But then we had the next escalation stage with transient execution attacks. Spectre Meltdown started that. Still a side channel was involved. They are not side channels, but a side channel is involved in these attacks. And now the big difference is they directly leak data. So you really can read content of your kernel, content from something else you're not supposed to read, but you still need a side channel to recover this data then. And now we are at this kind of final stage here, a very powerful one of architectural CPU vulnerabilities, where we get data out of the CPU from places we are not supposed to get, and we can do that directly without using any side channels, without using any timer measurements, just by doing interesting stuff with the CPU, as we will also see today. And this also started essentially with Intel SGX. So we've seen Spectre Meltdown, focusing on Intel. Intel SGX, a great product. I really like it. It's a trusted execution environment for those of you who don't know that. So you can write software, put it in there, and then it's supposed to be secure even if everything else is compromised. So you can have an operating system with rootkits and completely compromised, but the application you're running inside there is still secure. You can imagine that companies like Netflix really love that. But it's a really, really cool technique. And I also really like it, and academia liked it a lot, because it enabled a new type of research, because suddenly we had a different threat model to work with. Before that, for most of this exploitation, also you here do, you assume that you are unprivileged attacker, you maybe can run some code somewhere, and then you try to attack the operating system. But with TEs, you are now a much more powerful attacker. Suddenly, you can use everything an operating system can use, and you're not targeting the operating system anymore. You are the operating system, but you target this secure part here. And that gives you, well, a lot of cool primitives that you typically don't have for exploitation. So now you can play around with page faults, you can read performance counters, you can even work with very cool interfaces like undervolting your CPU from software, overvolting, changing frequencies. You can do a lot of things. And, well, this is incredibly strong. And you can imagine that if you have access to these things, people can get creative and find new ways of attacking a target. If you now can do way more than just running your unprivileged code. Well, this happened a lot. Intel SGX kind of fell into disgrace, especially in academia. It was used for a lot of these attacks because people showed like, okay, and if I use page faults, I get a new side channel. If I use performance counter, I get a new side channel, and I can extract some information out of that. And it was even considered like, please stop doing attacks on Intel SGX. It's like beating a dead horse. Don't do that. It's already lying on the ground and bleeding. It's like, academically speaking, for this side channel research was kind of broke. But also to be fair, this is not Intel's fault. Because SGX was designed before we have seen all these microarchitectural attacks. It was designed before Spectre, Meltdown, all these things. So they didn't know about these things and they didn't protect against it. So while it was broken with these things, well, not entirely their fault. And we also really liked using that, and we still like using these kind of things for research, because it enables us to do things that we otherwise can't do. And in the process of that, we start with attacks with that, because we have a lot of privileges for doing that, and then we try to reduce the privileges. And I've brought one of the first attacks that really got data out of SGX without using any side channels. So I tried to keep it high level. So essentially, and please anyone working on real CPUs, just don't listen now, it's kind of simplified. We have two parts here in this attack for Epic Leak. We have the one part, this is the Epic, the advanced programmable interrupt controller, which the operating can configure for interrupt stuff. It's a kind of a, well, it evolved from a legacy interface. So you have memory mapped registers that you can read, and they are very small. And then the manual says like, well, you can read these small registers, but there's more stuff memory mapped, but don't read that. You're not supposed to do that. If you do that, it's undefined behavior, don't do it. And well, the sane operating system also is not going to do that. But remember, we're in this scenario with transient-execution environments. The operating system is malicious now. So this is one part. Second part, the super queue is essentially an internal buffer inside the CPU, and every time you read data from memory or write data to memory, your data somehow goes through this buffer, and well, it has a copy of recently used data. Now, the interesting thing is, this of course also happens for SGX. Also, if you load data there, store data there, it also goes through this internal buffer, and you have recently used data inside this internal CPU buffer. And now the very interesting part is, for some CPUs, there's a kind of an implementation bug. Well, I don't know the details. But if you, as an attacker, now read from this memory mapped registers from this Epic that you're not supposed to read, it's like you really don't do that in the manual. So we did it. And if you read from that, you do get data back, and it's essentially data from the super queue. So you get your real data that you can read, so there's one register from this Epic, but the remaining bytes that you read here is stale data from previous data stores, data loads that happened on your system. So you directly get data back. And this is really, really easy to exploit. So this is essentially proof of concept code is like 4 lines. And you can start like an enclave now with protected content. Then you start this dumper where you read from these Epic regions, and then you directly get a lot of data back there. So if we scroll up here, we see on the top, this is the data, the text we've stored in the enclave, and it works with that, it converts it to uppercase internally. And we see the data we read is essentially the data we leak, except for always missing 4 bytes where we get the actual register content from the Epic, but everything after that is the data stored inside this trusted execution environment. So we have a direct read primitive into these things. This was like the first leak, architectural leak, where we really saw data coming from the CPU without having to do anything, just reading from a weird address we're not supposed to read. So this was all Intel. And I don't want to bash Intel, so I really like the company and their products. And still all that affected Intel in the beginning. And we had a different CPU vendor, AMD, and they were rather confident. So they were looking at all these things and saying like, they really produce bad CPUs, right? Aren't we the best? And they had this official statement, AMD believes that our hardware paging architecture and protection checks help AMD processors not be affected by many side channel vulnerabilities, regardless of whether simultaneous multi-threading is enabled or disabled. So like, we are the best, right? Marketing words. But we also had to tell them, well, threat models shift. So maybe you're not affected now, but you also evolve and you add new features to your CPU, and what happens then? So this is also what happened for AMD. So they also introduced the trusted execution environment. So the kind of equivalent to SGX, had a different model, so they did not have like an application running, but they decided to completely go for a virtual machine. They completely encrypt the virtual machine, protect that. So if you have other untrusted VMs or an untrusted hypervisor in the cloud, you can still run your VM on your favorite untrusted cloud provider, and they can't do anything. They don't see what you're doing. They can't manipulate. Well, they introduced that, and every time you introduce a new security feature, you have a lot of academics looking at that for fun and papers. And there were quite a few attacks already in the beginning. And now these were different types of attacks, kind of integrity attacks. So confidentiality was kind of given by encrypting everything. But for integrity, well, it was a bit different. So it was able to, for the hypervisor, to remap page tables and then get other content, downgrade firmware to vulnerable versions, and injecting code inside the guest. So you could not read something, but you could inject code, and well, you all know if you inject code somewhere that you control, then you can also use that code to read secrets. So there were a bunch of attacks on that. And that also led to the statement like, well, this secure encrypted virtualization, SEV, and the extended version of that are not designed to protect guest VM's memory integrity. It's only about confidentiality, right? So you can't read it. If you modify it, yeah, we're not protecting against that. So they kind of saw that as a bonus. But, well, if you've exploited things, you know if you can modify stuff, then also confidentiality will be gone because, as I said, if you like inject code, you can also read data. So we can't have that. We can't have confidentiality without integrity, and that also took a while at AMD to realize. So in the first version, they just encrypted the memory, forgot about registers, so it was possible to read and modify register content. In the second version, then they did that, but they forgot about paging structures. And then in the third iteration, with secure nested paging, they're like, okay, now we're done. Now we fixed everything. We have confidentiality and integrity. And again, public statement here. SEV S&P is designed to prevent software-based integrity attacks. Yay, finally. And reduce risk associated with compromised memory integrity. And then the important thing, how do they define that? The basic principle of SEV S&P integrity is that if a VM is able to read a private encrypted page of memory, it must always read the value it last wrote. Well, a bit of a complicated definition, but it makes sense. If you write something and you read it back, it should be the value you wrote. If it's a different one, you have a problem. So this was their guarantee that they gave. And it's like, oh, now it's becoming interesting. Because before that, it was kind of trivial to break. So it was not super interesting for us. But then we said, like, okay, interesting. So now it should be really secure. But did they consider all of the things that we have with this now shifted threat model that we are the hypervisor, we are a malicious hypervisor, and we can use whatever we want? And for all of you who have worked a bit more with x86, you have seen there are tons of instructions, and many of them are not used anymore, like kind of legacy instructions that are still there for backward compatibility, but, well, they're not used. And one of them looked very interesting. So the invalidate instruction. Who has used the invalidate instruction before? Nobody. Yeah, one. Exactly. You should not use that, right? So what is the definition of this invalidate instruction? It's a privileged one, so it can anyway only be used by operating system or hypervisor, and it flushes all internal CPU caches. But with this one thing, with this one property, it does not write modifications to memory. So you have things in your cache that are not yet in memory, and it still gets rid of that. And of course, this is not a great instruction to use in production code, right? And Intel also adds a big disclaimer to their manuals and like, use this instruction with care. Data cached internally and not written back to main memory will be lost. Software should instead use the write back invalidate instruction, which first writes the data back to memory and then clears the caches. So this is what's documented in the Intel manual. You don't find this disclaimer in the AMD manual. And they made sure that you cannot use that when you're using SGX, for example. AMD kind of forgot that an operating system can use that. Well, they did disable it, to be fair. But with a mechanism that the operating system can re-enable it again. So we re-enabled this instruction, and then we can do the following thing. I try to illustrate that here. So we have a hypervisor, which is malicious. We are the attacker. And we have a victim virtual machine that should be protected, like, confidentiality and integrity. And this victim VM does something very simple. It just prints a value, changes that, and then prints it again. So we see here what happens. The first time the victim VM tries to print that value, it's fetched from main memory, from the DRAM. A copy will be kept in the cache, and then it's printed to the output. And we get this value 3. Perfect. Then we modify that in the victim VM. We overwrite it with 4. If we do that, it's only updated in the cache for now, before it's at some point written back to memory. So we only have the modification inside the cache. Now, if we would print it again, we get the value from the cache, and it should be 4. But here we interrupt the victim. As the hypervisor, we use this invalidate instruction, which clears all the internal caches without writing anything back to memory. So cache content is gone. In the DRAM, we still have the old value of 3. And then resume the victim VM, and it happily fetches it from the DRAM, puts it in the cache, and outputs 3 again. Well, not great, right? It should be 4, it's 3. That definitely violates this integrity definition that we had from AMD. But also, a lot of people said, like, so what? Maybe a functional problem. But we are security people. So of course we can turn that into a security problem. And we did a very, very simple exploit to demonstrate that on sudo. So simplified, the code for sudo looks like that. It has this your user ID, it initializes it to 0, like any sane program initializes values. Then it calls this getUID to ask the operating system, like, what is the current user ID? And 0 is coincidentally also root. And it says, like, if it's root, then the sudo just continues, otherwise it asks for your password. All right, this is how it should work. And what we also see here, like, well, there's a store here where we get the value from the operating system and store it into the variable, like the store from the example before. If we invalidate that store, this line is essentially gone, and we are always root, because this is the default value of the UID. We are 0 now, we are root. Perfect. We can continue without being asked for a password, and we escalated our privileges with one single CPU instruction. Pretty nice. This was then, well, people were still skeptics, like, yeah, well, you're exploiting one specific behavior of one application. This is not a cool exploit technique, right? So we just modify sudo that it initializes it not to 0, but to something else, and then it's fixed. Like, okay, well, you want something more generic, and luckily I had quite a few CTF players in my, as PhDs in my team, and they really liked exploitation. And it's like, give us a day, we'll show you a very cool attack. Like, okay, sure. And this attack, they call it time warp. And this is really a bit brainfuck. So if you do exploitation, you know things are brainfuck already, but this is kind of next level. So I tried to make that simple here. I still need some assembly and some stack illustration to see what is really going on. So what we see here are essentially two functions, ret0 and ret1. What they do is return 0 and return 1 by moving the return value into this RAX register where it stores return values. What do we do in the program? We call return 1, so the return value is 1. Then, well, we have that here. Then we compare, is the return value 0, which of course will never happen because we just called the function that returns 1. And if this is the case, then we jump to our win function, we get our shell, whatever. Well, it's not going to happen, right? Because it's 1. And then we call return 0, which essentially sets the register to 0. And we would go back and jump to fail. But what we do now here is, after calling return 0, the CPU, of course, pushes the saved return address onto the stack. So after the return, after setting it to 0 and returning, well, we would go back to this jump instruction, right? And then we're done. But now with our attack, we call invalidate, and we just had to write the saved return address to the stack. This is a memory write. We invalidate that. So on the stack, we don't have the correct return address where the CPU should return to, but the stale one. And the stale one was from the last call. So if we do that, if we invalidate that, and then we return, we are essentially jumping back in time, and we are jumping back to the previous return location, which is after the call for red 1. So we're jumping back here. So now we change the control flow back to older control flow, but keeping the data with the new data. And now we have a 0 in the register. Compare that to 0. Yes, it's true. And yes, we win. Okay, I know this is a lot. And I just wanted to illustrate, like, okay, we can do really, really cool stuff now when we're not talking about just software exploitation, but involving hardware as well. Then we can come up with very interesting primitives. And you can imagine, this is a toy example, if you try to find things like that in real-world software, this is tricky. So where you can go back to a previous control flow with the new data and then being able to circumvent something. That requires a lot of thinking. But, well, I have some clever people in my team, so they did that on SSH, for example. So essentially, what you now do with this kind of exploit is you let the CPU execute until the store you don't want anymore. Then you flush the entire cache. Then you let the CPU kind of step over the store, like do the store. Then only the store is the modification in the cache. And then you throw away the cache content, the store is gone, and you reverted this one store. And then you hope you have a clever idea of how to exploit that. So that really gives us a very generic exploit primitive based on hardware oversight. That's completely independent. And of course, so AMD was not super convinced. It's like, yeah, okay, here's a patch. And they provided a microcode patch, and so like, okay, but now it's fine. We fixed that. That was a simple oversight. We forgot this instruction. Fixed. Now it's really secure. But every time somebody says that, in our team, there's somebody's like, really? Is it? And the same student, they're like, okay, let's test again what else we could do, what else they could have missed. Well, summary, he found stack warp, essentially another CPU vulnerability, which allows you to shift the stack pointer a bit. And this is probably also something for, if you're used to software exploitation, you can already see like, okay, if I can modify a stack pointer, yeah, that could be a powerful primitive. And now I don't need any buffer overflow or anything. I can directly do that via hardware, which gives us a very generic primitive. And this was exactly what he wanted to achieve. So he was very happy, my student, because this exploit keeps the VM running. It corrupts the state, so you can get his rob chain in there, and it can be triggered from outside the VM. So no code execution or anything was required for that. How does it work? Again, simplification. If you know a bit about exploitation, you know about the stack pointer, and you know if you, for example, push something onto the stack, then the stack pointer moves, and if you pop something from the stack, it moves again. This is what you see, but this is not the reality anymore. So what the CPUs do nowadays, it's basically all modern CPUs, they have a stack pointer, but they don't actually modify it. So if you push something onto the stack, then the stack pointer should move, but it doesn't. The CPU keeps an internal delta of the stack pointer that is stored in this register and the real one where it's supposed to be. So the CPU just keeps track of an offset and has its internal stack pointer, and as long as you don't try to access the stack pointer, it will not update. And only if the stack pointer really is red, because you're interested in the value, then the CPU synchronizes that, takes this internally tracked delta, and fixes the real register with the stack pointer content. So it looks like it's doing that all the time, but it's not. Secret of the CPU. And this is a very nice optimization, but also something that can be exploited by turning it off and on again and off and on. So we know it typically fixes things, but here it breaks things. So it's a very clever idea that my student had here. So like, okay, let's look at that. So we have the victim VM we want to exploit. We have an attacker spawned VM, and the hypervisor is also attacker controlled. In this attacker VM, we pop something from the stack. What happens then? Well, the stack pointer does not really move, but the delta inside the CPU is updated, and the CPU knows, like, okay, if somebody wants to use the stack pointer, I have to fix this, the real stack pointer with this delta. then the attacker in the hypervisor turns off the stack engine. So you can turn off that optimization because CPUs, also another secret, they have a lot of knobs to turn off features because CPU designers are not always 100% confident that stuff works. So they have options to disable some of the functionalities, especially optimizations. You can do that. You can turn it off because maybe it's not working correctly. And what happens then on AMD is this offset is frozen. It's not reset. It's frozen, and the stack engine is not involved anymore. Then you let the victim VM execute, like pushing something onto the stack. It puts it on the stack. Stack pointer is directly correct at the correct value. And then you switch back to your attacker, to the hypervisor, and the attacker turns on the stack engine again. So it's like, no, I want to have that optimization. It's actually pretty nice. That unfreezes this offset. And now if you switch back to the victim VM, the CPU is like, I have this offset here. I need to restore the real stack pointer. And it fixes the stack pointer. So now the stack pointer moves inside the victim VM. It's not supposed to do that, but this is what happens. And then if the victim VM pushes something again to the stack pointer is wrong, and it pushes to this already used location, and it corrupts its own stack. Pretty nice. Already quite complicated again. So we have a VM of the attacker, we have the hypervisor, it needs to be synchronized. We need to turn it on and off at the right time and push and pop the right amount of pushes and pops on the attacker side. But then we can essentially shift the stack point in any direction at any point of the victim execution. And this also was a bit easier to understand, and my CTF players in the team is like, okay, well, pretty cool. Corrupting data, we can easily do fault attacks on crypto. It's like the trivial thing. They had that in like 5 minutes. Then they did privilege escalation with sudo. They had kernel code execution. They had a rob chain in a network backhead and then modified the stack pointer in the kernel to go into this rob chain inside the network backhead, and then they had kernel code execution. So typical exploitation things then, but with this one difference, you now have the hardware with the vulnerability. So it's not like a buffer you can fix in software and it's fine, but the hardware gives you this primitive to modify the stack pointer and do these attacks. So pretty nice. Luckily also fixed now with the new CPUs. It's a good thing. And we did not stop there. So you could still say like, there's single incidents and it's only AMD, and AMD is really not good at these things. No comment on that. But we also moved to different vendors and also different architectures. And one of these things was Ghostwrite. Ghostwrite was also like a very fun hardware vulnerability inside the CPUs. It's now RISC-V, so completely different CPU architecture, but also they suffer from problems. So normally, if you've paid attention in like, your operating system classes, you know if you have your program writing to memory something, then you do that to a virtual address, then there's an address translation going from virtual address to physical address via page tables set up by the operating system. Inside the page tables you have this permission check, like are you really allowed to write to this address, otherwise you get a segmentation fault, and then it reaches physical memory. So this is a normal memory write, but then we had affected CPUs, had a very cool undocumented instruction, a vector write, and there they forgot to do all these things in between. So this undocumented vector write, which is in hardware, you can buy these CPUs and run this instruction. The CPU says like, I don't have this instruction, but you can execute it. Then you can do a store, and the store directly goes to physical memory. So essentially, from your unprivileged user program from within a virtual machine, you can specify a byte you want to write and a physical address, and it just writes there. Very nice, right? A perfect exploitation primitive. So we can directly write anything anywhere we want without any permission checks, even write to memory mapped I/O, so we can directly communicate with hardware if you want to. Was very nice, and there's no fix for that. So if you want to play around with that, get one of these boards. So we also see this is not an AMD problem or an x86 problem. This affects a bunch of CPUs. And we have super creative people here just looking at you. And we've seen that in the past for software exploitation. We see that now people find ways for exploiting even smallest mistakes. And if you look a bit past, we saw like this essentially all started with transient execution attacks with Spectre Meltdown, where people were convinced like, oh, the CPUs have security vulnerabilities. They are real. It started with side channels being involved in seeing them, but now we see more and more architectural things where you can directly read data, write data on a CPU. And this is a problem. So luckily, we don't have exploits now, I guess. So at least there's no real, well, reports about any of that. I haven't seen that. Will we have them in a few years? Maybe. So software security is still not the best, so we still have low-hanging fruit. But if we get more secure software, more secure systems, probably in a few years, we'll see them exploited in the wild. If someone builds automated tooling, like Metasploit for CPU vulnerabilities, I'm absolutely sure we will see widespread exploitation. So if you need a new hobby project, that could be it, right? What do we do? Can we do anything about that? Well, we have to find them before attackers exploit them, which is still in its infancy because testing CPUs is much more difficult than testing software. For software, we have a bunch of different techniques. For CPUs, we don't. And also CPU bugs are ugly. A software bug, well, it just crashes a program, you can directly see that, and it's local to one program. A CPU bug, on the other side, is super ugly. It refuses to crash. CPUs typically don't crash. They just continue in some weird state. You can often not even see that. It's just some behavior that then at some point appears. And it's on the CPU. It's not per program, so it can be an interaction of multiple programs, the operating system needed to trigger that. So this is kind of ugly. And also, testing is tricky, because for software we have these nice things, we have debuggers, we get feedback, we can emulate that, it crashes, it does not have laws of physics. For CPUs on the other side, we don't really have debuggers. With vendors, yes, but well, for us, no. Emulating them is slow, also for vendors. They don't really crash, as said. Everything happens in parallel, and there are also laws of physics involved, which doesn't make it easier. Still, we have some success in automated testing. We see some of the things are still found manually, some found it with automated help. I thought about like how many with AI, and I think it's 0 so far. So we're still good at that manually, but still in its infancy. And I hope this will change. So as a takeaway, CPUs must be treated like software. They have bugs, but they're just faster. They are harder to debug. They are deployed at massive scale, and it's a pain to update anything there. So we must make sure they don't have a lot of exploitable security vulnerabilities. We've also seen they are exploitable. So even if it's just some small thing, you have clever people finding a way of exploiting that. And that goes across all privilege boundaries typically, because CPUs don't care about processes or anything like that. And we still lack the way of testing that, because we really don't know the metrics, the observability, the strategies. So I hope if I give a keynote in 10 years, I can tell you like we've solved CPU testing and we found a lot of bugs and now we fix all of them. But I'm not super optimistic, but I hope I inspired some of you in working on that and finding ways for finding CPU bugs and fixing them. Thanks.
Thanks a lot. Thanks a lot, Michael.
Questions for Michael?
You have any question? We have time for 1 or 2 questions.
If you come back to one of the first slides, I think it was slide 8, you had Spectre, and you had old CPU, more recent CPU, and there are more vulnerabilities in more recent CPUs. Is it because some countermeasures can be bypassed or something like this? Can you comment on this?
Well, so you mean...
you had,
no, where was that?
Yes,
this one.
This one, yes. Spectre, right? You're more, right? So, I mean, Spectre is hopeless. We'll never fix it.
Yes.
On the more vulnerabilities we have are bypass of some countermeasures or something like this. Is it?
So yes, Spectre is kind of hopeless at the moment. So we know about that since 2017, which is now a long time. We don't really know how to fix it because like an inherent design issue. We like to have speculation, but we don't want to have the security problems, but solving that is tricky. So we'll keep them. But for the other things, we see we still have new vulnerabilities, but it's not that many. So if you look at this Intel Core Ultra 9, we essentially have just like 2 vulnerabilities that are not Spectre. But also the new ones typically affect, the new vulnerabilities affect the old CPUs, so we'll have a growing list here on the left. But yes, we'll also introduce more, and maybe also we see more on new CPUs because more and more people are working on that. So back then, in like 2017, we had a handful of people working on that, believing that CPUs are not secure, me included. Nowadays, you have quite a few research teams and also vendors. Internally, they look for a lot of bugs. So yes, we see in absolute numbers maybe more bugs, but it's also because we look more for them than we did in the past. But it's like the spiral. Also, the more people working on software exploitation, we see that in the number of CVEs, for example. We see more and more buffer overflows every year, but it's not because our software gets worse, but more people look for them and have more automated tools in finding them. Does that answer that?
Here. Thank you for the talk. Do CPU vendors have any tooling, internal tooling that they might be happy to share with security researchers, independent security researchers?
So first, I know that CPU vendors, of course, have internal tooling, but I also know that they are not eager in sharing things, like any things. Be it like how their CPU works, CPU source code, tooling and stuff like that. And if you also look at the reports, they do have a lot of internal findings. They also have very smart people internally because they unfortunately buy the good people from academia and then they work for the vendors. And they have a lot of internal findings, and you see that in the reports. They also like to have that. They have the reports saying like, most of the vulnerabilities we found internally. So I don't think they're super happy to share this tooling with anyone else, because then anyone else can find a lot of these things.
Last question. Last. Okay.
Hi. Thank you for your great talk. You may have answered to my question with the last question, but I have 2 questions in one. The first thing is the hardware vulnerabilities that you have shown are by design only exploitable locally, because it's local and physical and hardware vulnerabilities. And I wonder with the virtual machines that are in the hypervisor, if there is a possible remote exploitation by attackers. And my second question is, do you know if there is any tools that are developed to detect this kind of hardware vulnerabilities?
So, first understood correctly, like for this vulnerability so far, we need local code execution. We don't have any remote attacks yet, but I think this is just a matter of time. So we have also seen that in other attacks, right? You always start simple. So we have seen that for attacks, like CPU vulnerabilities, first attacks required you to be an operating system and then attack something else. And from that, people evolved and reduced the requirements. And for Ghostwrite, you can do that from within an unprivileged VM. So we see more and more than vulnerabilities that don't require these privileges anymore. We've also seen that for classically side channel attacks. We've seen that for Spectre. First thing, you do a local code execution, you exploit that. Then you have seen NetSpectre, for example, you do Spectre remotely. Took a bit, like 2 years. I'm pretty sure we will see similar things here as well. Right now, a lot of privileges, we will reduce them, and at some point, we will get remote attacks. And then it's extremely scary. Second part was about detecting that. I'm not aware of any things that really detect these kind of things. It's difficult. I mean, you could look at code, but this is like an antivirus software. If you change patterns, we know this problem. But also the threat model for some of these attacks is really strong. So if you're a malicious hypervisor, where do you run your detection software? So if you as a cloud provider decide to go rogue, and it's like, now I have all this interesting data running on my cloud, it's encrypted, but I make more money by leaking the data and selling it on the black market than by getting the money for hosting that, who's going to stop you? So it's a different threat model, and detecting that, well, not simple, because where is the detection running? You don't have a more privileged level where you can deploy that.
Okay, thank you, Michael. You have to stop now to switch to the next presentation. Thanks a lot again. Thanks.